Hi, welcome to my channel, JaberTime. Today I'm going to go over the cross product in 3-dimension and vector calculus. I have some pictures right here to get you started, and I'm trying to make it as quick as possible, hopefully less than half an hour. So let's get into it. The cross product, it's called a vector product. Last time video was the dot product, which is a scalar. This one is a vector product. So if you have A as A1, A2, A3, and B as B1, B2, B3, the cross product is as follows. I don't want to read it. It's kind of lengthy, and it's hard to memorize it. So you don't need to memorize it. As I said, I want to go a little bit fast to save you some time. You could go back and visit and pause the video anytime you want. So let's explain where this is coming from. So if you have A as A1i plus A2j plus A3k and B in the same way, the cross product comes from the determinant, setting the components this way. If you remember from previous classes in calculus and more, when we do the determinant, if we go with the first row, we go plus, minus, plus. I'm highlighting the minus sign right here, so just be careful. So to do the I part, you cover the first row and you cover the first column, and you go A2, B3 minus B2, A3, or the determinant of this 4 elements, minus, you cover the J column and or the second column and the first row, you get A1, B1, and you get A3, B3 on the second one, and so on. So if you do the multiplication, this is exactly what you have. So look at this one here, A2, B3, A2, B3, minus A3, B2, minus A3, B2. So that's where they're coming from. You don't need to memorize it. You just do the determinant of a 3 by 3. A quick example. 1, 3, 4. As stated, 2, 7, negative 5. I with the minus. Don't forget the minus. 3, 4, 7, negative 5. Those, they go here. And to do it, you multiply 3 times negative 5, which is negative 15. You go back and subtract 7 times 4, which is 28. And the rest continues, all right? Show that A cross A is 0 for any vector A in V3. Here's A. And if you want to do the cross product of A times A, I have it displayed twice. You do the math, and as you could see in different colors, I have 3 components, but A2, A3, and A3, A2 are the same. With the minus sign, they're gonna cancel. Same thing here, same thing here. So it is 0 for any 2 or any vector multiplied by itself. Of course, as you go, you'll understand more why these things happen. The right-hand rule, or the going from X to Y, or from A to B, the cross product will point in the Z direction. You can't go the other way. See the arrow right here? Going this way with your hand, you're pointing up. So that's the direction of the cross product. It's a vector, and it's pointing out of the plane that contains the 2 original vectors A and B. So the vectors, or A and B, are vectors right here in this case. The vector A cross B, the cross product, is orthogonal to both A and B, which means that we have a 90 degree here between the blue and A, you see the 90 degree? Also, the cross product, the blue one, is perpendicular to B. Well, it is perpendicular to the plane that contains A and B, so it's going to be perpendicular to both A and B. To see that, we're going to use what we know from the dot product from the previous section. The dot product between the blue one, which is A cross B, and A will be as follows. You just do the components. This is the first component of the cross. This is the first component of the cross. The second component. This is the third component of the cross. And you just multiply. And if you simplify, you just take your time and simplify. Everything cancels. And I'm telling you which ones cancels. The red cancels. The green ones cancels. And the light blue cancels. Everything cancels. So it's 0. In the same way, if you could do the cross product with B, that will give you 0. The graph says it, but if you want to take your time and do it, that's what we have. If theta is the angle between A and B, and theta is between 0 and pi, including 0 and pi, then the cross product is the magnitude of A times the magnitude of B times sine the angle in between. We had a similar one in the dot product. It was a cosine, if you remember. So now we have two formulas for the cross product, the one that comes from the determinant and the one that involves the angle in between. So since we have this, if this is 0 and A is not 0 and B is not 0, two non-zero vectors A and B we have will be parallel if and only if the cross product is 0. Well, if they are parallel, that means the angle in between is 0, or you could say pi the other way around. So sine 0 is 0, which means the cross product is 0. Okay? So just because they don't have an angle in between, this will be 0, confirming that they are parallel. Find a vector perpendicular to the plane that contains these 3 points. Well, to find a vector perpendicular, you need to do a cross product. But I don't see the vectors, I see points. So we're going to make the points, or the vectors. If you go from P to Q as a vector, you subtract -2 minus 1, that's -3, 5 minus 4, which is 1, -1 minus 6, which is -7k. That's PQ. PR will be the same concept. Let's take a look at the first one. 1 minus 1 is 0. There is no I, as you can see. So now we have two vectors. They start at the same point. You do the cross product. There is another practice. And the cross product will be perpendicular to the plane that contains these two vectors, which means the plane that contains these 3 points. So the perpendicular vector is this. But as you can see, 15 and -15 and -4, they all divide by 5. So you could simplify it, but you don't have to. It says find a vector. So any vector will do. Here's another vector. Any non-zero scalar multiple of this vector such that is also perpendicular to the plane. Here's some quick notes. We know that when you go this way, I cross J will take you to K. There is more than that. If you take your time and look at it, sometimes it's a little bit hard to think backwards and think on the other directions of X and Y and Z, but I have them listed for you. You could just give it a try. The cross product is not commutative. It makes sense. X cross Y will give you Z. or give you direction in Z. If you go Y cross X, your hand will be upside down, and you're going to point to Z minus, or the negative Z axis. Okay? Instead of saying Y cross X, I'm going to say J cross I. It's right there. So J cross I will point down instead of up. That means I cross J is not the same as J cross I. In dot product, it's commutative because it does make sense. You just add the components, and when you apply the first component to the second component, doesn't matter if you do it the other way around. It's commutative. In cross product, no, it's not commutative. I cross J. This right here is K, and this is how you move on. So I cross K, you have to think about how it looks like in the graph and move your hand. You're going to go through the negative y-axis. That's called minus J. Of course, we know this. That was listed a few minutes ago. A cross A is 0. In this case, I cross I acts like A cross A. So 0 cross J will be 0. The associative law for multiplication does not usually hold. So just sometimes it might, but when they say generally, that means you cannot depend on it as a rule. What's interesting about the cross product, it has some benefits. This parallelogram formed by the vectors A and B with an angle in between has this height, and this height from a right triangle is the opposite, and the opposite could be written in terms of the hypotenuse as the magnitude of B times sine theta. You could derive this yourself by saying sine theta equals opposite over hypotenuse, then solve for the opposite, and that's what you get. So the area will be, for this shape, base times height, and the base as a length is magnitude of A, and the height is shown. Because we want area, we want the cross product, because that's a cross product. Now it's base times height. It's the same thing. But if you want it to be all as an area positive, you want to make sure that you apply the magnitude or absolute value, whatever you want to call it. That's called magnitude. So the cross product magnitude or length of that vector that we said it points usually towards the positive z-axis will give you area, the amount of area that you form as a parallelogram with the vectors down in the xy axis of A and B. So that's one benefit of the cross product. It gives you a magnitude. It points up, just in case, you're referring to the basic graph, and also represents the area of the parallelogram. A short, quick example. Find the area of the triangle. Now, this is a triangle, it's not a parallelogram, but just wait, you'll see. So I have 3 points. We'll make the two vectors A and B. The way we do it, do the cross product, but the cross product magnitude will give you the area of the parallelogram. The length or the magnitude of this cross product will give you the area of the whole thing, the parallelogram. But since we want the triangle, we just divide by 2. As I said, maybe I'm going too fast, but I want to save you some time, and you could just go back as notes and you see it clearly. There's some properties that I don't want to skip in the lecture video because I call my videos lecture videos, not just examples. So you don't have to go fully to the book back and see what I missed. I cover it all with examples, but sometimes I have to go a little bit fast because I don't want to make my videos close to 1 hour. That is what I mean. Those are properties where C is a scalar. I use different color to highlight between this C and this C. This is a vector. This is a scalar. All right. A cross B is in the opposite direction of B cross A. We know this, right? Take some time and look at this, or pause the video if you want. What's interesting also, that your book or any calculus book focuses on the fifth one. It's called triple product. A dot and a cross. A dot, the cross of B cross C, will be A cross B dot C. But this is called triple product. That's what they call it. What is the triple product and how do you do it? This is how you do it. So if you have B cross C, you put the B's right here and the C's here and A in the front, and you do the determinant, and that's it. This is a scalar. It's a number, it's not a vector. Here's what's interesting about the triple product. You see this graph right here? I have B and C and another vector A. Down here, I have B cross C. But if you do the cross product, B cross C magnitude, that will give you the area down here for this parallelogram. Now, if you want the volume of this, you don't go times A, you go times the height. But the height, looking at this right triangle, this is a right angle, is the projection of this vector onto the z-axis. And if you look at it sideways, this is the adjacent of angle theta, which means cosine theta. We're going to use not sine. It's the magnitude of A times cosine theta will give you this. This is called the scalar projection, which was covered on last video too. So the height is absolute value of A, or magnitude of A, times cosine theta magnitude. The reason why we're using magnitude of cosine theta, because we want to make sure that this value is positive. In case theta goes beyond 90 degree, cosine is negative. So that's what we have. Imagine this is graph the other way around. So you're going to have the angle. It could be, it's kind of hard to imagine it more than 90 degree, how it's going to look like. But just to be on the safe side, because we want height, apply the absolute value to both. Now, the volume is base times height. The whole base right here. This is the base, magnitude of the cross product, and the height is the component or the scalar projection, as we mentioned. But here's what's interesting. Put this up front, rearrange, and you'll have this. I don't have to color it anymore. You have a magnitude of a vector, a magnitude of another vector times cosine theta between them. But that is a dot product, because the dot product between two vectors A and B is actually the same way. Magnitude of A times magnitude of B times cosine theta between them. But that's the angle between this and this. The cross product is right there, and the angle between A and the cross product is right there. So that is a dot product, because we want volume. Keep the magnitude to be on the safe side, and that should do it. All right. Use the scalar triple product, which is a scalar, just to emphasize, to show that these three vectors are coplanar. Coplanar means they live on the same plane. They don't go off in 3D. All right. As I said, quick and easy. I don't want to take the time and show you how to multiply and how to subtract and how to add, but let's consider it lecture with notes. This is the triple scalar product. You just display the numbers. Instead of writing them as your book writes it, here and here and here, I kind of wrote them aligned so you could see it quick and easy to move to the matrix. Don't forget the minus sign. This minus came with the -7, so it's not a minus. It's like plus -7. So do the math. It's 0. What does it mean? We know something, that the magnitude of that scalar dot product represents the volume. But we have 0. So imagine a shape like the one we saw but has a volume of 0. That means they are actually staying on the plane. They're not going off and making a 3D dimension figure. Okay, here's some applications for the cross product, and we'll close this video with that and an example. Torque. The idea of a cross product occurs often in physics. In particular, we consider a force F acting on a rigid body at a point given by a position vector r. This is a position vector r, and this is what we have in the figure. Clearly shows with the wrench. We're gonna twist it this way. That's my force. That's my angle from the position vector. And the torque is gonna be directed this way because we are actually tightening, and it's gonna take that direction. For instance, if we tighten a bolt by applying a force to a wrench as it shows, we produce a turning effect. The torque T, or small t, relative to the origin is defined to be the cross product between R and F. So if you do F right here and you do the cross product, think about it. This is F, and you go from this way to this way with your right hand, with your hand. This is where you're going to point, which makes sense. You're going to go in the wall, if you will call it that way. So that's how we do it. It's a cross product. So this is the formula for the torque. The magnitude will be just the magnitude of the cross product, and the cross product uses sine, not cosine. Just keep that in mind, and that should do it. A bolt is tightened by applying a 40 N force to 0.25 M wrench. Find the magnitude of the torque about the center of the bolt. I have 75 degrees. I have 40 N, 0.25 M. All what you need to do, the magnitude, they want the magnitude, that's the magnitude, do the cross product between R and F, include the angle as it says, 0.25, 40, that's what we have, and that should do it. Trying the best that I can to make it less than 30 minutes videos. I think it's easier to watch and come back to instead of 45 minutes. These lectures, some of them, they have notes. So if I slow down on the notes, it's gonna take more time from me and you. But hopefully that was helpful. And I have another one right after this. Okay? So I'm recording another video for the coming section, and I will be uploading 2 videos this morning. Thank you for watching. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.